All right, so welcome everyone. This is our class or our tutorial for P192 tutorial sheet 2, which is consisting of questions on a specific heat capacity and also the specific latent heat. So without wasting much time, let's get into it. And we start with question 1, which is having three parts. But A is saying a 400-watt element is used to boil 500 grams of water in a cup. The initial temperature of the water is 25 degrees Celsius. Take the specific capacity of water to be 4,200 joules per kg Kelvin. Question 1. How long will it take to reach 100 degrees Celsius? How long will it take to reach 100 degrees Celsius? Question 2 is stating any assumptions that you have made whilst solving this problem. Okay, so this question is very, very straightforward. And we've been asked how long, which means we're supposed to calculate the time. Which means I'm going to say time here. We don't know, but we're looking for the time which it's going to take for this water to heat up from 25 degrees Celsius to 100 degrees Celsius like this. So they've given us the specific capacity of water. Say that's 4,200 kilojoules. Is it joules? Okay, so it's joules per kg Kelvin. 4,200 joules per kg Kelvin. Yeah, so I'll say kg Kelvin. Kg Kelvin like this. And so is the power of 400 watts. Okay, so this is the data that we've been given, and we're supposed to calculate the time it's going to take to heat this temperature, or to heat this water rather, from 25 degrees Celsius to 100 degrees Celsius. So first things first, to say the formula for finding the amount of energy absorbed to heat up a substance, we say Q is equal to the mass of that particular substance multiplied by the specific capacity of that particular substance, which in this case is water, multiplied by the change in temperature. And they've already given us the mass also to say it's 500 grams. So I'll just put here, mass is equal to 500 grams, which is also 0.5 kilograms like this. Okay, so since our specific capacity has been given in kilograms, it means we're also going to convert our mass of the water into kilograms. So first things first, what are we going to do? We are going to find this energy that is required to heat up the water from 25 degrees Celsius to 100 degrees Celsius. Then when we are done with that, we're going to use the relationship between the power that is being supplied by this element to the heat absorbed, which is the Q here, and the time that it's taken. So that equation is the one that we're going to use to find the time it takes to heat up the water from 25 degrees Celsius to 100 degrees Celsius. So which that relationship is to say the power supplied is equal to the heat that is absorbed over the time that it takes. So we can just rearrange this formula to say the time that it takes to heat up this water from a certain temperature will be equal to the heat that is absorbed over the power that is being supplied. So this is the formula that we're going to ultimately use to find the time that it takes to heat up this water. So let's find the Q first, and we're going to say Q is equal to Q will be equal to M, which is the mass, 0.5 kilograms, multiplied by the specific capacity, which is 4,200 joules per kg Kelvin, multiplied by the change in temperature. So the change in temperature, or when you're looking at the change in temperature scales between the Kelvin and the degree Celsius, it's the same. It's the same. So they've told us to say our given temperatures are in degrees Celsius, but our specific capacity is containing a unit of Kelvin. So what you have to understand is that when there's change in temperature between the two temperature scales, the degree Celsius and the Kelvin, the change in temperature is the same. There's no difference. So we can still use degrees Celsius, and we're going to get the answer, which is very, very much correct. So the difference in temperature will be the final temperature, which is 100, minus the initial temperature, which is 25, and this is in degrees Celsius. So the kg here and this kg here can cancel out. Then you can also cancel out this degrees Celsius, which is the unit of measurement of temperature here, with this Kelvin that is here. Okay, so I'm going to say 0.5 multiplied by 4,200 joules multiplied by the temperature difference, which is 75, and I'm going to get Q, which is equal to 15,000 or 157,000 500 joules. So this is the amount of energy that is absorbed to change the temperature of our water from 25 degrees Celsius to 100 degrees Celsius. Now that we found the Q, let's just plug it into this formula and find the time that it takes. So time, just write it here. Time will be equal to the Q, which is 157,500 divided by 400 watts. And this is going to give me a time which is equal to 393, 393.75, 393.75 seconds. So the time that it takes for the water to heat up from 25 degrees Celsius to 100 degrees Celsius with a power supply of 400 watts is actually 393.75 seconds, of which you can just also round this off to the nearest whole number to get 394 seconds. So that is the time, ladies and gentlemen. And our question 2 was asking to say, what kind of assumptions are you going to make during this procedure or during this calculation, or to be able to conduct this calculation? So one of the assumptions we're going to make is that there should be no heat that is lost to the surrounding. We have to assume that all the heat that is supplied is actually absorbed by the water to take part to this temperature change. Because if you've noticed how I've solved, I didn't mention any heat that was lost. I just assumed to say no heat was lost to the surrounding, hence it was all absorbed by the water. So that is one of the assumptions that you are going to make. And also you have to consider, or you have to assume to say the specific capacity of water is actually going to remain constant over all these steps, or over the rise in temperature. Over the period where there is rise in temperature, your specific capacity should actually remain constant. You should also assume that there is no phase change. I didn't mention any latent heat here, which means there is no amount of heat that is going to be absorbed to change the state of this particular water from whatever state to another. So we have to assume that the state of this substance, which in this case is the water, is remaining the same. And should also assume that the heating is actually taking place uniformly. So those are some of the assumptions that you can actually include in your assignment. So that was question 1, part A. We can move on to the next question, which is part B. Part B saying a coil carries an electrical current of 4 amps for 110 seconds at a voltage of 30 volts. If this is sufficient to boil away 25 grams of liquid nitrogen at its boiling point, what is the specific latent heat of vaporization of nitrogen? Okay, so a heating coil carries an electrical current of 4.0 or 4 amps for 110 seconds at a voltage of 30 volts. If this is sufficient to boil away 25 grams of liquid nitrogen at its boiling point, what is the specific latent heat of vaporization of nitrogen? So in order for us to solve this question, this is also not very complicated. We're just going to actually use the relationship between electrical energy and heat energy required for a phase change, of which in this case the phase change is vaporization. So this is question B. Tell me that's question B. We've been given current, which is 4 amps. We've been given voltage of 30 watts. We've been given time, 110 seconds. We've also been given the mass of liquid nitrogen to be 25 grams, of which I can convert this into kilograms immediately to say this is 0.025 kilograms. And what I was supposed to find? We're supposed to find the latent heat of vaporization of liquid nitrogen, the LV. So first things first, what are we going to do? We're going to find the electrical energy. Since I said we're supposed to use the relationship between the electrical energy and the heat energy, one thing we should understand is that the electrical energy that is supplied is going to be converted into heat energy so that it does the work here, which is vaporizing this liquid nitrogen. So when we are given this data, voltage, current, time, mass, and we're looking for latent heat of vaporization, the first thing we're going to do is find the electrical energy that is supplied. So the energy that is supplied in the coil, Q, will be equal to what? Will be equal to voltage multiplied by current multiplied by time, like that. So our Q will be equal to 30 multiplied by 4 multiplied by, let me just put across, 110, which means our Q, which is supplied in this case, is equal to 13,200 joules. 13,200 joules. So 13,200 joules is the energy that is supplied to the liquid nitrogen. And since we found the energy, this is now as simple as drinking water, because we're just going to apply the formula for finding energy absorbed to change the state of the liquid nitrogen from liquid to vapor, of which we're going to say Q is equal to mass of the liquid nitrogen, multiplied by the latent heat of vaporization, like that. So if I'm looking for the latent heat of vaporization, I'm just going to divide both sides by mass. Hence, I'm going to have my latent heat of vaporization being equal to Q over mass, of which this is equal to 13,200 joules divided by the mass, which is 0.025 kilograms, like this. Hence, I'm going to get my LV. Just write it on the left. I'm going to get my LV as 13,200 joules divided by 0.025 kilograms. And this is actually going to give me 58 or 52, 8,000 joules per kg. So the latent heat of vaporization of our liquid nitrogen is actually 528,000 joules per kilogram. So that is all on question B. Question 1, part B. Let's move on to part C. Part C is saying an electric current of 5 amps flowing through an electric heating element of resistance 6 ohms embedded in 100 or in 1200 grams of an oil. Raise the temperature of the oil by 15 degrees in 12 or 15 degrees Celsius in 12 seconds. Calculate the specific heat capacity of the oil. Calculate the specific heat capacity of the oil. So still on specific heat capacity. This is part C. And we've been given current of 5 amps. We've been given resistance of 6 ohms. We've been given mass of the oil as 1200 grams, which is directly converting to 1.2 kilograms. Converting to 1.2 kilograms, and they've also given us a change in temperature, which I'm just going to call this delta T of 15 degrees Celsius, like this. Okay, so we're supposed to calculate C, which is the specific capacity of the oil. I'll say this is equal to question mark, like that. So the first things first, we're going to find as we did in part B, we are going to calculate the electrical energy that is supplied, because the electrical energy that is supplied is the one which is going to be converted into heat energy. So what am I going to do? I'm going to say electrical energy, bearing we've been given current, resistance, and time. We're going to say electrical energy, which is going to be directly converted to heat energy, will be equal to current squared multiplied by resistance multiplied by time. This is the formula for finding heat, provided the things that will be given. So learn how to differentiate the formula that we used in part B and then this one. So the heat is going to be equal to the current squared, which will be 5 squared multiplied by 6 multiplied by the time. Did I include the time on my data? No, I didn't include the time, but they've given us time to say the heating actually just took place for 12 seconds. So this multiplied by 12 seconds, and our Q will be equal to 1800 joules. 1800 joules is the heat that is supplied, or is the electrical energy that is supplied, of which that electrical energy is directly converting to heat energy that will be used to heat up this oil. So we found the heat that this oil is going to absorb now. So what are we going to do? We're going to bring the formula for heat absorbed, provided the specific heat capacity. So Q is equal to M multiplied by C multiplied by change in T, of which this is going to be equal to the mass Well, first, let's make C the subject to the formula. Since we're looking for C, I'm going to divide by M over multiplied by delta T. Even here, M multiplied by delta T. So M will cancel out, delta T and delta T will cancel out. So that means my specific heat capacity of oil will be equal to Q, which is the heat supplied, divided by mass multiplied by the delta T. This is going to be equal to 1800 joules over the mass, which is 1.2 kilograms, multiplied by the change in temperature, which is just 15 degrees Celsius, like that. So this is going to directly translate to, let me try and manipulate the denominators first. Okay, so I'm going to get 1800 joules over 18. This is just 18 kgs degrees Celsius, like that. So if I divide this, I'm going to get my specific capacity of oil as being equal to 100 joules per kg degree Celsius. 100 joules per kg degree Celsius, like this. So this is the specific capacity of the oil that has been given in this scenario, and thus we are done with part C of question 1, which also marks the conclusion of question 1. Let's move to the next question, which is question 2. And question 2 is stating to say a block of copper at 100 degrees Celsius is placed in 128 grams of water at 30 degrees Celsius. The specific heat capacity or the specific heat of water is 1 calorie per gram degree Celsius, and the specific capacity of copper is 0.1 calorie per gram degree Celsius. If the temperature of the thermal equilibrium is 36 degrees Celsius, determine the mass of the copper. If the temperature of equilibrium is 36 degrees Celsius, determine the mass of the copper. So there are how many processes taking place? We have been given copper at 100 degrees Celsius, and it has been placed in 128 grams of 30 degrees Celsius water. And we are supposed to calculate the mass of the water. We're supposed to determine the mass of the water. So we're going to use the same knowledge that I taught you when I was talking about thermal equilibrium. In order for you to reach thermal equilibrium, because one substance will be heating up, whilst one substance will be cooling up. So we'll be using the knowledge that we acquired when the lesson on specific heat capacity. If you haven't watched that video, just go down the description or go down and check the videos on my YouTube. You are going to find that lesson. We're going to use that knowledge on specific heat capacity and thermal equilibrium. So we have been given two substances here. This is question 2, part A. We've been given two substances here. The first substance is the copper. The first substance is the copper, and the copper has the initial temperature. I'm going to say T0 of copper, which is 100 degrees Celsius. Then I have T0 of the water, which is 30 degrees Celsius. We've been given T final, which is the equilibrium temperature, to be 36 degrees Celsius. And what else? They've given us the specific capacity of water. So we have the C of water, we have the C of the copper. The specific capacity of water is 1 calorie. 1 calorie per gram degree Celsius. Then the specific capacity of the copper is 0.1 calories per gram degree Celsius, like that. What else? They've also given us the mass of the water. Say this is equal to 128 grams. So since they've given us specific capacities in grams, where it's not necessary for us to convert the mass of water from grams to kilogram, since the units they've used here are both grams. We can just work with it like that. Then we're looking for the mass of the copper, of which we don't know. So what are we going to do here? we know to say when two substances are mixed, in order for the equilibrium temperature to be reached, we're going to say the amount of heat that is gained is equal to the amount of heat that is lost. Like that. So this is the formula that we are going to use in order for us to find the mass of water. So the water will be gaining the thermal energy, whilst the copper will be losing the thermal energy. So what are we going to do here? We are going to find these two guys, the heat that is gained and the heat that is lost. And how is that going to be? Let's do this. The heat that is gained on the other side will be on the side where there is water, this side. Whilst here we are having our copper. So I'm going to say on this side, the mass of the water multiplied by the specific heat capacity of the water multiplied by the change in temperature will be equal to, so I said when heat is being lost, you can write this equation in two forms. It's either you're going to put the negative in front, then you put everything else in brackets like this. Or if not, you can just swap what is here on the change in temperature so that you don't have to deal with the negative. So I'm going to say this is equal to mass of water of the copper on the other side multiplied by the specific capacity of the water. I mean the copper, sorry. This is the copper multiplied by the change in temperature. So for now, let's assume there's still a negative in front. Okay, so we can start plugging what we have into this formula because we've been given the mass of water to be 128 grams multiplied by the specific capacity of water, which is 1 calorie per gram degree Celsius, multiplied by the change in temperature. And the change in temperature is equal to what? It's equal to final temperature minus initial temperature. So this will be the final temperature, which is the equilibrium temperature, 36 minus 30, like this. And this is going to be equal to what? This is going to be equal to the mass of the copper that we're trying to calculate, multiplied by the specific capacity of the water, of the copper rather, which is 0.1 calorie per gram degree Celsius, multiplied by the change in temperature. So I said, if I have gotten rid of the negative which was in front here, that means in the brackets here, I'm going to swap. Instead of me saying T final minus T initial, I know to say the initial temperature is higher than the final temperature. So if I do it like this, I'm going to get a negative inside the brackets here. And this negative which is here is going to cancel out with the negative that is there. So in short, I'm just going to say T initial minus T final. So the T initial is what? The T initial is 100 minus 36, like that. What we're looking for is the mass of the copper. So I'll continue. I'll multiply what is here. Here I have my 6, so I'm going to say 128. The gram and the gram are going to cancel out here. The degree Celsius on the temperature and the degree Celsius here are going to cancel out. So I'm going to remain with what? I'm going to remain with 128 multiplied by 1 calorie multiplied by 6, which is the temperature difference, which is going to give me 768 calories, being equal to the mass of the copper multiplied by I have degree Celsius here, or the temperature difference is going to be equal to 100 minus 36. This is 64. So I have 64 in my brackets there. I'm going to say 0.1 calorie per gram degree Celsius, of which the degree Celsius can cancel out with the degree Celsius, which is here. I'm remaining with 0.1 calorie per gram multiplied by 64. And what am I getting by so doing? On the left-hand side, I'm getting 6.4 calories per gram, like this. So this is the formula that I'm remaining. And the thing that I'm trying to calculate is the mass of my copper. So I can just divide both sides by 6.4 calories. Even this side, 6.4 calories, like that. This is per gram. Even this side, I can just put per gram. So this will cancel out like this. I'm remaining with my mass of my copper to be equal to 868 calories divided by 6.4. And this is going to give me exactly 120 grams of copper. So that's the final answer. 120 grams of copper are available in this systematic exchange of thermal energy. So that is all on part A of question 2. Okay, now move on to the next question, of course, which is question 3. And question 3 has 2 questions. The first one is saying what would be the final temperature of the mixture when 10 grams of ice at negative 15 degrees Celsius is mixed with 40 grams of water at 30 degrees Celsius? Specific capacity of ice is 0.5 calories per gram degree Celsius. Latent heat of water, 80 calories per gram. And this specific capacity of water at 1 calorie per gram. So what are we going to do to solve this question? This is a very, very simple question. A very simple one, actually. So we can solve this one using 2 methods, because we're just trying to find the equilibrium, or we're going to use the principle of equilibrium temperature. They're asking us to find the final temperature. So we're going to use the principle of equilibrium temperature. So this is question 3. Question 3, and there are 2 methods that we can use here. It's either we can use that same one for saying Q n is equal to Q lost, where on this other side, we're going to have how many Qs? We're going to have Q that is used to change or to raise the temperature of the ice from negative to 0. So we're going to call Q1 plus Q2, which is the temperature that is used to change the phase of the ice, plus Q3, which would be the energy that is used to raise the temperature from 0 degrees Celsius to the final equilibrium temperature. And this should be equal to Q4. But this formula is going to work best if we know whether it's the ice that is, or if it's the liquid water which is going to turn into ice, or if it's the ice that is going to turn into liquid water. So you can use this one. It works very well, and it's the one that I taught when I was talking about equilibrium temperature. But let's use this other one so that we at least talk about both the methods that you can use to solve such kinds of questions. So the first thing we're going to do is we're going to find the amount of energy that is here, that is used on the right hand side, and we're also going to find the amount of energy. We're going to try and so find the amount of energy that is going to take to change the temperature of the liquid water from its initial temperature to 0 degrees Celsius. And we're going to compare the 2 sides of temperatures and see the amount of energy which is going to be more. The one which will be in excess, we're going to find the difference between the two, and therefore be able to calculate the equilibrium temperature. So let's do this. Let's find the amount of the heat required to raise the temperature of ice from negative 15 degrees to 0. So ice, that's the first thing I'm going to talk about. Let's reserve this method. Let's use the other one. We're going to say Q required to raise the temperature of ice from negative 15 degrees Celsius to 0 degrees Celsius. So this is going to be equal to what? This is going to be equal to, I'll call this Q1 as usual. It's going to be equal to MC of ice multiplied by the change in temperature. And this is going to be equal to the mass of the ice that they've given us. Say it's 10 grams. Give us 10 grams of ice multiplied by the specific capacity of ice, which is 0.5, multiplied by the change in temperature, which is 0 minus negative 15. 0 minus negative 15, like this. So this is going to be equal to what? This is going to be equal to 10 multiplied by 0.5 multiplied by 15. Negative and negative make a positive. Therefore, Q1 will be equal to what? Q1 will be equal to 75 calories. 75 calories. So this is Q1, the amount of heat energy that is required to heat the temperature or to change the temperature of the ice from negative 15 degrees Celsius to 0 degrees Celsius. Now let's find the amount of energy that is required to change the state of the ice, of which we're going to call that Q2, and this is equal to the mass of the ice, which is 10, multiplied by the latent heat of fusion, of which they've given us the latent heat of fusion would be 80. So this is equal to what? This is equal to 800 calories. So these are the two energies on the left side of the equation. The energy that is supposed to be gained to change the temperature of the ice from negative 15 degrees Celsius to liquid water at 0 degrees Celsius will be the summation of these two, 75 calories plus 800 calories. And this is going to give us what? Q1 plus Q2. This was going to give us 875 calories. So this is the energy that is required to propel the left-hand side of our equation into liquid water. Now, let's go to the right-hand side of the equation. Let's find the heat available from, the heat that is available from warm water cooling from 30 degrees Celsius to 0 degrees Celsius. So I'll put my line here. The heat that is available from the 30 degrees Celsius water changing to 0 degrees Celsius, this one will be equal to Q, will be equal to the mass of the water multiplied by the specific capacity of water multiplied by the change in temperature, like that. So the mass of the water is 40 multiplied by the specific capacity of water, which is 1, multiplied by the temperature change, which is 30, minus 0. So this one is going to give us 30. And the Q, and I can call it Q3, is actually equal to 1,200 calories. So from here now, you can see to say this energy, the heat energy that is available to change the temperature of water from 30 degrees Celsius to 0 degrees Celsius is more than the heat energy that is required to change the temperature of ice from negative 15 degrees Celsius to liquid water at 0 degrees Celsius. So what are we going to do? We're going to find the heat that is going to remain if we change our state of the ice from negative 15 degrees Celsius to liquid water at 0 degrees Celsius. So we're going to say the heat remaining. This is, I didn't teach this in my previous tutorial, so I want you to really understand this one. And I'm going to use the same one on the last part also so that we fully understand it. So I'm going to say Q that is remaining will be equal to 1,200 minus 875. These are calories. So this is going to give me how much? This is going to give me 325 calories. Like this. So this is the Q that is remaining. Now, this heat now is the one that is going to raise the temperature of the resulting 50 grams of water. The ice that has melted and the liquid water, we're adding the two masses to come up with 50 grams of water from 0 degrees Celsius to the equilibrium temperature, which is the T final that we don't know. So from 0 degrees Celsius, the combined water into the equilibrium temperature T final that we don't know is going to be raised due to the presence of this energy that has remained after the difference between the one that is required and the one which is available. I hope you really understand that statement. So I'm going to say my Q will be equal to mass of the water multiplied by the specific capacity of the water multiplied by the change in temperature. So this is going to be equal to what? It's going to be equal to the mass of the water. And which mass of the water are we talking about? It's the 10 grams of the ice plus the 40 grams of the liquid water that we already had. So in total, we're having 50 grams, like this, multiplied by the specific capacity. And they've given us the specific capacity as 1, multiplied by the change in T, of which the change in T is equal to what? The change in T is T final minus T initial, of which T initial is 0. So we're just remaining with T final here. So I'll say multiplied by T final, like this. Okay, so this is Q remaining. So the value of Q remaining that we found was 325, and this is going to be equal to 50 multiplied by 1. So 50 multiplied by 1, this will be equal to 50 T final, like this. And if we divide both sides by 50, even this side by 50, I'm going to get my final temperature, which is the equilibrium temperature T final, being equal to what? Being equal to 6.5 degrees Celsius. And just like that, ladies and gentlemen, you will have found your equilibrium temperature. Very simple if you understand this method, but if you don't want to use this method, use that previous one that we used in class. And it's going to give you exactly the same answer. I just want you to understand this one so that you are also able to apply it where necessary. So the only thing you're supposed to follow is first find the energy that is required to change the state of your ice from negative 15 degrees Celsius to liquid water at 0 degrees Celsius. Then go to your right-hand side of the equation and find the assumed energy that is required to, or that is going to be released when you change the temperature of your water from 30 degrees Celsius to 0 degrees Celsius. Then find the difference between the two, and that remaining thermal energy is the one that will be responsible for changing the combined temperature of the water now from 0 degrees Celsius to the equilibrium temperature, which we don't know in this case, the T-fine. And you use this approach to find your equilibrium temperature. So that was question 3A. Let's now go to question 3B. Question 3B is saying a mass of 12 grams of ice at 0 degrees Celsius is placed in a drink of mass 210 grams at 25 degrees Celsius. Calculate the temperature at thermal equilibrium given that the specific latent heat of fusion of ice is 334 kilojoules per kg, and the specific capacity of water and the drink is 4.2 kilojoules per kg Kelvin. Per kg Kelvin. Okay, so we're going to apply the same method that we used. First things first, let's gather the data that we've been given. So this is question 3B. This is question 3B. And question 3B, they've given us ice, 12 grams of ice, or which you can convert this into kilograms. Then you have 0.012 kilograms of ice. They've also given us the initial temperature of ice, T0 of ice. Say this is 0 degrees Celsius. They've given us the drink, and there's mass of the drink, which is 210 grams, which is the same as 0.21 kgs, like that. And we also have the initial temperature of the drink to be 25 degrees Celsius, like that. They've given us, or we are looking for the final temperature, T final, and they've also given us the specific latent heat of fusion of ice. So LF of ice is 334 kilojoules per kg. They've also given us the specific heat capacity of the drink, and they've given us a C of the drink to be equal to 4.2 kilojoules per kg Kelvin, like this. So we're going to apply the same method that we used in the previous question. The ice is already at 0 degrees Celsius, so it only needs latent heat for it to melt from ice to liquid water. So we're going to find the amount of energy that is used on the, or that is required on the left-hand side of the equation, and we're also going to find the amount of energy that is produced on the right-hand side of the equation if the temperature is reduced from the initial temperature to 0 degrees Celsius. Then we'll find the difference between those two and plug them into that equation that we had at first. So I'm going to say here, since the ice is already at 0 degrees Celsius, that means it only needs the thermal energy in order for it to change state from ice to liquid water. So Q will be equal to mLF. So this is Q1. So my Q1 will be equal to the mass of the ice is 0.012 multiplied by the latent heat of fusion, which is 334 kilojoules per kg. So the kg and the kg here are going to cancel out. The kg and the kg that is here are going to cancel out like that. That means I'm going to have 0.012 multiplied by 334. So this is in kilojoules, which means even my answer Q1 will be in kilojoules. And this is giving me exactly 4.008 kilojoules. So this is the amount of energy that is required on the left-hand side. So we know to say Q again is equal to Q lost. Okay, so this is the amount of energy that is required there. Then now let's calculate the maximum heat that is available when cooling the drink from 25 degrees Celsius to 0 degrees Celsius. So we're going to say Q, or which I'm going to call it Q2. This will be equal to the mass of the drink multiplied by the specific heat capacity of the drink multiplied by the change in temperature, of which here we are finding the maximum amount of heat available if the drink was if the drink was to go to 0 degrees Celsius. So I'm going to say my Q2 will be equal to the mass of my drink, which is 0.21 kilograms, multiplied by the specific heat capacity, which is 4.2 2 kilojoules per kg degrees Celsius multiplied by the change in temperature. So the change in temperature is 25 minus 0. So I'll just say 25 degrees Celsius. So the degree Celsius and the degree Celsius here will cancel out. The kg here and the kg here will cancel out. So which means my Q2 will be equal to 0.21 multiplied by 4.2 multiplied by 25. So this is going to be equal to 22.05 kilojoules. Okay, so this is the maximum energy, the maximum heat energy that is available if the drink was to cool down all the way to 0 degrees Celsius. So let's now find the remaining heat after melting the ice. The remaining heat after melting the ice, which I'm going to label as Q remaining, this will be equal to 22.05 minus 4.008, like this, and we're getting remaining heat as 18.042 kilojoules. Okay, so if that is the amount of heat that is remaining, let's now plug this into or rather, this is the amount of heat that will be responsible for raising the temperature of the mixture of the ice and drink from 0 degrees Celsius to its final equilibrium temperature. So what are we going to say? We're going to say Q, which is this same remaining Q. This will be equal to mass multiplied by specific capacity multiplied by the T final, of which here, to say this is the same as the T final minus 0. So I'll just put T final there. So this is going to be equal to the mass, of which this is the combined mass of the drink and the water. So if I add the mass of the drink, which is 0.210 kilograms, plus the mass of the water, which is 0.012 kilograms, this is going to give me 0.222 kilograms. So I'm putting 0.222 kilograms here, multiplied by the specific heat capacity, and they've given us the specific heat capacity. So it's 4.2 kilojoules per kg degree Celsius multiplied by the change in temperature, or the equilibrium temperature, which we don't know. So we're going to label it as the T final, like that. Okay, so on the left hand side, what do we have? We have this same amount of energy, which is 18.042 kilojoules, like that. Okay, so my T final will be equal to this divided by 0.222 multiplied by 4.2, like that. Hence, my T final is going to be equal to 19.35 degrees Celsius. 19.35 degrees Celsius. As simple as that. So make sure you master this method. It's also very, very simple, and it's simple, I can say. So, ladies and gentlemen, that is it. That's all on tutorial sheet 2. We've solved all the questions, and please leave a like, subscribe to the channel, and also share this video with your fellows so that all of you will benefit equally. Passing is all about a group and not an individual. Making it in university is all about a group and not individually. So until next time, and make sure to register with our academy. I've put the details in the description for you to either download our mobile app from Google Play Store or register from our website. So thank you very much, guys. Until next time, stay blessed.